I had started the second section of the course, which has the title Electric Potential. And where I'd left off is right at the very bottom of page 4 here. I talked a little bit about how vacuum tubes work, which is not entirely an obsolete, useless thing to know, because for one thing, it'll come up in some of the labs I can think of at least one lab that we do in this course. And it is something that's still out there in certain specialty applications too. But moving on from that, the relationship between the E vector and potential difference. They're both ways of describing the strength of the field, okay? The E vector is the force per unit charge. The potential difference is the work done per unit charge. So they're both different ways of looking at kind of the same thing. I had mentioned somewhere the other day, I believe, that when I first introduced, what was that? Back up here near the top of the page, the unit for the electric field vector, newtons per coulomb, is equivalent to volts per meter. So just based on the units, you would expect that volts per meter times meters equals volts. And that is the short version of the story of what's the connection between potential difference and the electric field vector. Well, of course, there's always a way to make a simple thing more elaborate looking. And I did decide to go ahead and get some updated transparencies made, but I just sent them off this morning and I didn't get them back yet. So the old transparency here looks slightly different than the one you've got in front of you in the handout. But what if the field is not uniform? Okay. We're imagining moving a test charge from point A to point B. Delta V is the potential difference between these 2 points, A and B. Well, remember how far apart the field lines are is what describes, I should probably have the microphone over here since that's where I seem to be standing. How far apart the field lines are is how you represent the strength of the field. So the field is stronger on the left and weaker on the right. And so if you go moving the charge from A to B, as you go from one point to another, the field is constantly changing. The force on our test charge there is constantly changing. So instead of just volts per meter times meters, you have to take the entire displacement from A to B, chop it up into lots of little pieces, each of which is small enough that the field is approximately constant. You do volts per meter times meters for each of those little pieces, and then add it all up. In other words, you integrate. You take the limit of infinitely many, infinitely small displacements. And so ds is measured in meters. That's the tiny little bit that your test charge moves. That's the meters times the volts per meter. You integrate from A to B. There's also a matter of a minus sign, which is more trouble to explain than what it comes down to is by delta V, do you mean VB minus VA or do you mean VA minus VB? So the way I've got it set up here anyhow, where it's B minus A, there'd be a minus sign. So in general, the so-called voltage between these 2 points is negative integral of E dot ds. If the field is constant, then there's no need to chop it up into infinitesimals. You can just say the field times the distance, the dot product of E dot S, where S is the displacement vector and E is the field vector. Where you would get a uniform field, a field that's the same everywhere, is between parallel plates, or to be precise, infinite parallel plates. Well, of course, if they were truly infinite, it would be kind of hard to get them in through the door and set them up in here. But as a practical matter, what it means is you've got a couple of metal plates seen here in cross section. Okay, these are two horizontal sheets of metal. You're interested in the field between them, and the point where you're interested in the field is much farther from the edges of the plates than the distance. You know, maybe it's this point right here where you want to talk about the strength of the field. From that point to either of the plates is a much smaller distance than the distance to any of the edges. Okay, if the edges are really far away, it makes the math easier just to say they're infinitely far away. And so as long as you're not close to the edges, it's a good approximation to reality. When you get near the edges of the plates, the field lines start to bow outward instead of being straight and evenly spaced like I've got them drawn there. So if D is the distance from one plate to the other, volts per meter times meter is E times V, or if you want to turn it the other way around, E equals volts divided by meters, which is, you know, if you got a set of parallel plates, that's the convenient way of figuring out the strength of the field in there. You just come along with a ruler and measure how far apart the plates are. You stick a $15 voltmeter on there, and that tells you how many volts are across there. And volts divided by meters, that's the E field. So a few examples making use of this. Got a set of, oh, this reminds me. One situation where you'll encounter this is in lab number 3. Now, with lab number 3, it's the same situation as, we already did this once before with the gravitation constant lab that we did last fall, okay? Because it's a relatively expensive setup, rather than spend twice as much money and get 6 of them, actually I have 3, but only 2 of them are going to be available tomorrow. So anyhow, point is, on Friday, day after tomorrow, half the class will do lab number 2, half the class will do lab number 3. And then a week later, you switch. And what else was I going to say? Oh, back to this. Well, a little more what to expect also. Number 3, Millikan's oil drop experiment, where you measure the charge of the electron. You can expect to spend pretty much the whole period gathering data. I've got the calculations set up for you in a spreadsheet. Maybe half an hour at the end or something like that to write it up, but it's mostly going to be a matter of getting good at running the equipment and collecting as much data as possible. The other one, lab number 2, the actual experimental part of it takes like 5 or 10 minutes, and the rest of it is the calculations, most of which is in Microsoft Excel. If you're any good with spreadsheets, you actually could get that set up ahead of time and get in and out of here pretty quick. But what got me started on all that in the first place is the chamber where you do the experiment in number 3, the Millikan experiment. You've got 2 metal plates, and you're going to measure how far apart they are, actually with a micrometer, not a ruler, but same general idea. And you hook up a meter and you measure, I think we usually have like 250 or 300 volts or something like that across there. And it's just volts divided by meters gives you volts per meter. So we're doing the same thing here in number 2, except the numbers are different. So that's the volts. You convert that to meters. That will tell you the strength of the electric field, E. Next, just like in the quiz here, F equals Q times E. That'll tell you the force on the electron. And then once you know the force, F equals ma, that's the acceleration. So that's the strategy. The details go like this. A little less glare on the blackboard so that it shows up better in the recording. Okay. .500 volts. Separated by 0.006 meters. (83,300 volts per meter). That's the strength of the field between these two metal plates. The force experienced by an electron in this field, well, I'm not trying to keep track of the directions of anything here. The question doesn't give me enough information to handle the directions. We don't know if this field points up, down, right, left, or sideways. So I'm just interested in the magnitude of the force. The magnitude of a vector is a positive number, which is, before anybody asks, the reason I left out the minus sign on the charge of the electron. Only need to worry about minus signs if you're keeping track of the directions. Magnitude is just a positive number. A volt per meter is the same thing as a Newton per coulomb. I wrote it like that just so you could see that newtons per coulomb times coulombs is going to give you newtons for the force. 1.33 times 10 to the negative 14 of a newton. And then finally, F equals ma to get the acceleration. Now, 10 to the negative 14th of a newton doesn't sound like an awful lot of force. It certainly wouldn't be if that force acted on you, but electrons don't have a whole lot of mass at all. 9.11 times 10 to the negative 31 kilograms. You can look that up in your your reference handout in the same table where the Coulomb's law constant and the charge of the electron and some other things like that are listed there. 1.46. So 10 to the 16th meters per second squared, which is a lot of acceleration. Maybe for a little perspective, the acceleration due to gravity, of course, is around 10 to the 1 meters per second. You get up approaching 10 to the 2 meters per second squared, and that's where fighter pilots start to black out. And this is like 100 trillion times more than that. This would be very unhealthy if a human being experienced it, but of course electrons are a lot more rugged than people are. You have a question? Oh, okay. Just making sure. Potential difference between, number 3 now. Potential difference between point A and B. A is up here in the second quadrant, B is down here in the fourth quadrant. You've got a horizontal field. So the basic idea, once again, is it's asking for how many volts is the potential difference between those points. The basic idea, once again, is that volts per meter times meters gives you volts. But the little detail that this is meant to emphasize is that because it's a dot product, it's only the meters along the field lines that count. Any distance across the field doesn't matter. You get the same sort of thing with gravitational, but remember, potential is just potential energy per unit charge. So if you want to talk about gravitational potential energy, if you want to know the difference in potential energy between here and over here, all that matters is the distance along the field lines. Gravitational field in this room points down. The distance across the field lines doesn't matter. The difference in potential energy is just mgh, where h is the vertical distance. And it's the same kind of thing here. Point A is 3 meters to the left of the origin. Point B is 1 meter to the right of the origin. So you've got 4 meters there times the 1500 volts per meter. So the answer is going to be 6,000 volts. That's the general idea. If you want to go through it, the step-by-step picky details kind of go like this. So delta V, the integral, minus actually the integral from A to B of E dot ds. Now this is what's called a path integral. You're taking some sort of a path from A to B and chopping it up into little infinitesimal pieces. You have to have a path in mind. Okay, what path do you imagine a test charge following from point A to point B? Well, you get to pick whatever seems convenient, because I don't know if you remember the details, the obscure details of what the terminology means, but electric fields are an example of a conservative force field. And a conservative force field means that the work done between any 2 points is the same no matter what path you follow. So, because it's a conservative force, I did mention this, it was the section on work and energy in Physics 131. There might actually be somebody in the room who remembers that. Anyhow, because electric forces are conservative force, is a conservative force, any path is okay. And what seems easiest to me, here's point A, here's point B. I say, let's go along horizontally over to, I guess I'll call that point C. Once you get to point C, let's go right straight down parallel to the y-axis like that. There's actually kind of a similar problem in the homework. It's got two parts. One part of the problem says to get the potential difference between the 2 points by following a path like this one. And then the other part says to do it over again, get the potential difference between the 2 points by following a straight, a diagonal straight line from one point to the other. When you do it that way, you have to include the cosine of the angle because you're however many degrees it comes out. And you get the same answer doing it either way. But doing it this way, an integral is just a type of summation. And a summation can always be split up into a couple of smaller summations. It's like 1 plus 2 plus 3 plus 4 is equal to 1 plus 2 plus 3 plus 4. That's what I'm doing here. Integral from A to B is the integral from A to C plus the integral from C to B. In each case, the electric field is a constant all through the whole picture. It's 1500 volts per meter and has the same direction. Constants can be taken out in front of the integral. So we've got E dotted with that plus E dotted with So because E is constant, I can move it out in front of the integral. Integral of ds is just s. You just add up the length of all those little infinitesimal pieces, and you get the total length of the line segment. And that's good. I'll just be another minute or so. So volts per meter times meters times the cosine of the angle in between. As you go along the path from A to C, the displacement and the field are parallel. They make a 0-degree angle. As you go from C to B, the displacement and the field make a 90-degree angle. The cosine of 90 is equal to 0. So like I was saying, how much you move across the field lines doesn't matter because of the cosine factor in the dot product. 1500 volts per meter. Cosine is equal to 1. Distance from A to C is 4 meters. Potential difference is 6,000 volts because, well, I'll write that down next time. I've already kind of overstayed my welcome here. But the potential is decreasing if you go from A to B. If you went the other way, B to A, potential would be increasing and it would come out positive. See you Friday.